So in this lecture, I want to talk a little bit about my experience as a fatigue analyst in the automotive industry. And this has been a little while ago. I was hired as a durability engineer in the CAE group at midsize car division in the mid 1990s. Okay, so I realize at the time, even I'm recording this, this is a good while back, but I really suspect that a lot of things haven't changed in that industry. And I think this is pretty common to the ground vehicle industry in general, as well as other industries too. Okay. So I want to talk a little bit about the context of the vehicle design process and then kind of draw into the fatigue analysis perspective. So you want to have a vehicle. So somebody says we need a new model. And so there's all kinds of things that go into this before you actually use a graphics or a CAD package to come up with what goes in your vehicle design. So there are market studies, consumer input, and all these different things. There could be any number of different things that go into influencing what this vehicle's functionality might be. Is it a SUV? Is it a minivan? Is it a small car, a performance car? All these things kind of go into that process very early on in the vehicle design process. Eventually, it gets to a designer. Okay, so what does that mean? Typically, pretty early on, when these things have been determined, then you have somebody make a mock-up of this vehicle, and basically it's made out of clay. People like to look at things that are full size. Maybe these days they're using computer renderings, but there's something about being able to walk around an object and look at it from different angles and kind of get an idea of what that thing is going to be that you may not be able to do in a virtual design space or looking at renderings or just paper drawings. So the designer comes up with a clay model. At the same time, that there's the designer's model, then usually there's an engineer's clay model as well. Okay, well, how might the designer's clay model and the engineer's clay model be different? Well, maybe the engineer knows that if you're going to put a certain size engine in a performance car, you need to have the hood be a certain length. Or the designer may say, I need my hood to have this angle, and the hood has to kind of bend down this way, and that'll make it look really nice. Well, the two have to finally get together and decide physically what the actual dimensions of this thing are going to be. Okay, so there's some back and forth in determining where this is going to end up. And then once that's determined, then the final model is frozen, clay is frozen, after these differences are reconciled. So basically you have an outer design envelope physically for what this vehicle is going to look like. And through this process, there's usually one engineer that is the vehicle chief engineer. They have control over every aspect of that vehicle from the engineering perspective. Nothing can be done to that vehicle without them approving of it or their signs approving of it. So they're kind of like, I don't know, the king of the car. The chief engineer has a bunch of release engineers. Okay, so the release engineers would be responsible for certain sections or subsections of that vehicle. So you might have somebody for the vehicle's chassis. You may have another one for the engine cradle, the wheelhouse, whatever different subcomponents you can think of, the engine compartment, there would be these different release engineers. And these release engineers, they're responsible for everything that goes on inside of that space. So if you're uh, looking at the engine compartment area, so that may be the washer bottle and the battery tray and all those different things that are in that space. You may not think about it as a consumer, but somebody has to figure out where those are going to fit in, where those things are going to go, how they're going to interface with other parts of the vehicle, and what the allowable tolerances are, and the manufacturing details, everything that goes on inside that particular space. So the release engineers are actually really important engineers that make that section, that vehicle, work out. Kind of underneath the release engineers, then you would get into the particulars of analysts. So you might have an FEA person, you might have a vibrations person, you might have a test person, where they do a lab test or a road test. You might have a manufacturing person. If you're doing body, you may end up spot welding a lot of things on that body, so you need to have an interface with all those things. And any number of different branches that can come off of here as well. So the vehicle release engineer takes into account all these different other engineers' input into what is the right material to use, what's the right shape, what's the right design, and in conjunction with what that product is supposed to deliver, then they take care of that space and then report to the vehicle chief engineer. The chief engineer is usually assigned to that vehicle for the entire lifetime, and them or one of the release engineers would be taking care of any recalls that may occur during that life of that vehicle and so on. So these are usually very key people at kind of predictable points in their career where they know a whole lot. Maybe they were an FEA analyst to begin with, or a durability analyst. They became a release engineer and then got promoted up to vehicle chief engineer. As you might expect, there's not a whole lot of vehicle chief engineers. Basically it goes with the model or the family of the vehicle. You're probably aware different vehicles get branded under different nameplates, but they're basically the same vehicle with different variations. So General Motors has reconfigured a little bit, but there was a time when Pontiac was around, and your Pontiac and your Chevrolet had a kind of the same car, but slightly different flavors. Like Camaro and Firebird or whatever. These things you might see for these different vehicles. So let's go ahead and add durability engineer in here, since we're talking about our fatigue analysis class. And we can kind of talk about now, what does the typical durability engineer do in a company like General Motors? Again, based on my experience, things may have changed somewhat over the last years, but like I said, I don't think things would change that much. So your typical durability engineer would usually have some idea of a lot of these other things that go on in these other areas. Testing, manufacturing, finite element analysis. We know all those different things can influence the durability of the component. So although you may be kind of at the same level as one another, but you have to rely on the things that all of these people provide to be able to do a good durability calculation, and that may include analyzing test data and looking at test reports. You also have to have a good relationship with the actual component designer. So what do I mean by a component designer? So there may be one person that is tasked with coming up with the shape, form, and so forth, the CAD drawings of a particular component. Maybe it's a control arm in the car. All right, so I'm going to draw some sort of generic component. It's not going to be a control arm. But maybe it's some sort of brace or bracket. I'm just drawing something real simple. And even that I had a little bit of a hard time with here. Okay, so the designer for that component may not be an engineer. They may know some basics. They may be able to do even some calculations and say, based on the size of this, and I know it's going to be sheet metal, so these are the sizes that I have to use, 1 millimeter, half a millimeter, whatever it needs to be, and they may put a profile in it because they have experience with bending, and they may even know about moments of inertias and things like that. But they don't necessarily do a lot of sophisticated stress analysis. I think in some ways this may be changing as finite element codes get to be maybe easier for the non-engineer to use. But there's also some things you have to watch out for when anybody can do those kind of calculations. All right, so they come up with this component, and typically it's a CAD drawing. Well, there's different things you can do with this CAD drawing in order to do an engineering analysis on it. And the automotive industry in particular is very focused on finite element analysis. You can do some simple calculations, but the components that are in vehicles are typically more complicated than a simple mechanics and materials approach can be used for. So there's a lot of sophisticated CAE tools. So they would typically send this to a FEA person. Now the same CAD drawing might be used for a vibrations person. And the vibrations person may also be using finite element analysis, but they may have different mesh sizes that they like to use. They may have different mesh requirements that are used. Even in the FEA analyst side of things, you may have a standardized element size that you use for your company. Sometimes the durability analyst needs to really look at that data and say, you know, in order to get a good fatigue analysis, I may have to refine the mesh. Now this meshing is kind of an art form in itself. If you've taken my class, Applied Finite Element Analysis, we talk about ways to make a good mesh, what a good mesh looks like. And in a way, you can be an engineer and make a mesh. You can also have kind of an artistic flair for it with an understanding of where element mesh densities may need to be smaller. There are auto meshing algorithms. The fatigue analyst may not like those in some cases, but there's different ways to do this. And even in the 1990s, typically what would happen would be the designer would send the CAD drawing to some facility in another country across the other side of the world. maybe in India, sometimes maybe China, and someone there would do the actual meshing. And some of this meshing is extremely detailed. So if you see a little simple component like this, you could say, oh, no problem, I can do that. But when you're talking about every single component in 2 dimensions or sometimes 3-dimensional solid elements for a vehicle, that is really quite a task. So they will outsource this to specialty companies, specialty people, maybe at a cost savings if you're in a different economy, where they could turn this around and basically the FEA analyst can have a meshed part to perform his analysis on, his or her analysis on, the next day. Okay, so you leave work at 5 o'clock your time, it's 8 o'clock in the morning somewhere else in the world. They get this meshed. By the time you get back at 8 o'clock in the morning your time, then you have this nice meshed component that you can deal with. Now, where do we get the loads and things from? Well, the FEA analyst may just be looking at strength, so they may have certain standards. They may have loads from the loads group. So there's a piece of software called Atoms. It's a dynamics analysis program we call loads prediction. In some instances, you can use measurements on either existing vehicles or what they call a mule vehicle. So a mule is a cross between a donkey and a horse. Okay, so a mule vehicle is you take an existing vehicle that looks similar to the one that's going to come out, and maybe you modify the suspension and put your new suspension in the old vehicle frame or body, and then you do your measurement. So you can have your loads measurements in that way. Okay, so from a simplified chart point of view, and we could populate this with any number of inputs as well. But if we're designing some sort of component or subsystem, well, the designer has a lot of input, and they iterate back and forth. You may do some testing, and because of the testing, the component subsystem may change. There may be manufacturing limitations on how that subsystem or component must look in order for it to be able to be manufactured at a reasonable cost or price. And of course, there's the analysts that go back and forth and say, you know, this has to be increased in thickness or size in order for it to be a good type of component. And there's a whole lot of back and forth. There's trade-offs and compromises. But in the end, you end up with a component or subsystem design that the vehicle release engineer certifies. Says, let's go forward, this is what it's going to be. Now, as far as the fatigue analyst, I can make a similar kind of chart for what goes into the fatigue analyst's life. So I'm going to put the fatigue analysis here in the center of my little picture. Well, certainly all the things that we've talked about in class are pertinent to fatigue analysis, and even more than what we've been able to talk about. So certainly material properties will have an input into what goes on in the analysis. Your stress analysis, your stresses and your strains and so forth, those will all go into it. You may have NVH, noise, vibration, and handling. Okay, so the vibrations and the noise and all that may be directly input to the fatigue analysis. That can also kind of be going back and forth with the service loads. There's kind of a close coupling with NVH and the service loads. But definitely you need some kind of loads in order to do your fatigue analysis. The service loads themselves may be obtained from testing. Kind of put this over here. And I'm going to show this as kind of a separate track. The service loads that the testing people get can be used in the fatigue analysis, but in the end, what you're really trying to do as an analyst is you're trying to come up with a fatigue life calculation of that component. And with the testing, you're trying to do the same thing. So a good day in the fatigue analyst's life is when your calculation or your prediction matches what the tests say it's going to be within a reasonable expectation. And that reasonable expectation sometimes needs to be managed. Now, the durability engineer himself or herself, their role may evolve as the design progresses. In the early phase, you may have loads determination, target life estimation, materials and manufacturing to look at. So if you know that a manufacturing process is detrimental to fatigue life, you may have to speak up in a meeting and say, no, we really need to have this manufacturing process, or in some cases, as you saw in the recent video by our fellow student, the repair process may have to be altered in order to give an acceptable fatigue life. You may have to speak up about all these things. In kind of the middle phase of this process, you might have finite element analysis for durability, design iterations to save mass and so forth, the mule testing, prototype testing, updated loads and life targets may come about. And kind of in the later stages, you may get some sort of component, subsystem, or full vehicle tests. And then there's always often last-minute fixes that have to take place. So if your plastic battery tray develops a crack and breaks, then you need to figure out what's going on. Is it a problem in the manufacturing process? Is it a problem in your fatigue life calculations? Is the battery heavier than what was expected? You know, what's going on in that particular case? And a battery tray was one of the things I had to look at General Motors. So at each of these phases, the durability engineer has to interface with these different specific experts in all these different areas. And in a way, that's a really nice thing for a fatigue analyst to be positioned to maybe eventually become the release engineer for that particular subsystem. Because you're working with all these different people, you're not so necessarily narrowly siloed. You get to have all these different connections. You get to learn a lot about how all these different things can affect the fatigue life. There's typically another group in the automotive company that has a lot of input like the fatigue analyst does, at least from my perspective, and that is the vehicle crash engineer. Crash performance is mandated by the federal government, so there are specific requirements that have to take place under certain testing conditions. You know, there's a barrier test, and there's an offset test, and all these things that there are that you can do for crash testing. And that is also another type of engineer that interfaces with all these different areas. The loads may be different, maybe not looking at necessarily at long time histories or vibratory histories, but maybe impact type loading. There's lots of testing and analysis and so forth that goes on with those. So you'll often see crash engineers be promoted into the release engineering area. All right, one last thing I wanted to talk a little bit about was typical proving grounds. And so at proving grounds, they serve multiple purposes. There's ride and handling, noise and vibration, crash testing, durability testing. There's electromagnetic testing, low temperature testing, and all these different things. And I had the great privilege to be able to work at General Motors Proving Grounds in Milford, Michigan, for a few summers as a summer student intern there. I also worked in Warren, Michigan, at the main tech center for General Motors. And so, again, while most of what I talk about will be drawn from my experience there, uh, different automotive companies and different companies in general, particularly in the ground vehicle industry, have similar types of setups. General Motors typically has one of the more extensive proving ground systems. And so in our literature folder, I want to share with you a few things that are in here. And some of these I've pulled off of the web at one time or another that I can share. So this is an aerial view of the Milford Proving Grounds here. It's really a huge, huge area in kind of central southern Michigan. Even with this, you can see the large oval that they have here. There's a military proving ground area. Um, there's different hills, twists, and so forth. So I would encourage you to take a look through this, and we can kind of flip through this page, these couple pages that we have here. But it shows the early days of the proving grounds and so forth, going back 100 years, getting close to the 100-year anniversary in different cars. So looks like here's a '67 Buick Electra. But there's some interesting things that you can read about that. Let's see. So GM's Milford Proving Grounds 90th birthday. This was in 2014. There's this patch right here that's called the Black Lake. So they actually have problems with geese and other migrating birds that go and they try to land on this because from the air it shimmers so much with the heat coming off of it. It looks like water to them. So they try to land on it. So here's the straightaway and the turns for the straightaway. I've been actually been able to drive, was driven on some of this. I was friends with one of the groundskeepers. And they were able to show me some different things in different parts of the proving grounds. In the hills, you can't really see it from this perspective, but the steepest grade that they do the testing on is just seems amazingly steep from somebody who just drives on normal roads. From that perspective. So if you have a big heavy truck and you want to make sure it can take the grade with what it has in it, then that's a place where they can test that. And again, there's more information about the proving grounds. Here apparently was an old version of that, and here's maybe a more modern picture of a truck going through a twist ditch. So a twist ditch is one of the durability schedules. So what it does is it imparts a twist on the frame by a ditch going across the road at an angle. And so that is really a severe type of way to drive a car. All that torsion on the structure can be fairly severe. So sometimes you'll see people taking a speed bump and they all always kind of get over to one side because they want one side of the car not to take the bump. And when I think about it, I always take the bump straight on. I'd rather not have all that twist going on in my vehicle frame. But different people do different things. So, and again, another thing from the 75th anniversary. So you can read some of that. There are certain days of the year, at least they would have people, workers and their families come out. They could go fishing in the lakes and so forth. GM Proving Grounds in World War II. Some of these pictures didn't come through, but they have a vehicle division and they have a tank division. So General Dynamics often works building the tanks, and they get tested in the General Motors Proving Grounds. Now, Milford, Michigan is not the only place that they have proving grounds. They may not have this facility anymore. I can't remember, but they had a desert proving grounds in Arizona, and so Yuma, Arizona, they were testing the Chevrolet Volt. So particularly with electric cars, the ambient temperature can have an effect on the power that you can get out of your car. So they would want to test this someplace where they could have realistic high temperature conditions. They also have or had a cold temperature test facility in Minnesota. So they can do climate controlled tests at the Milford Proving Grounds by putting a car in a special chamber, but they can also do that kind of testing outside in a place that's cold enough. There's also Pikes Peak in Colorado. Again, I don't know for sure if that's still around, but there's high altitude testing. So there's all kinds of interesting proving grounds, and so I wanted to share some of that with you. I would encourage you to take a look at the literature, and it should be already on our box folder. Even facilities like the Mercedes-Benz facility in Tuscaloosa has a small test track with it. It's not a full durability test track, but it has a certain size test track. So let me save this. And I want to talk a little bit about the durability schedule for a vehicle. And basically, how long is the vehicle going to last? Maybe the first question you should really ask is, how long should it last? Do you want a car that never breaks? Could you design one that never breaks? But if you could, should you have one that never breaks? And what I mean by breaks is the chassis, the physical components. And the answer to that is probably not. If you have a 50-year-old car and you compare it to a car that's made today, there's a lot of improvements, safety improvements, electronics improvements, you name it. Any number of improvements have been made over the last 50 years. So maybe you really don't want a car that lasts forever because you don't want the old car driving on the same road as the new car. I suspect that in the future there's going to be more electric cars. I think that's pretty much going to happen. But not only that, I suspect there's going to be a lot of communication between cars and in the surroundings and other cars. How is an automated highway going to work properly if you have some cars that are smart cars and some cars that are dumb cars? And by that I mean the ability to communicate with one another. I'll relate a problem that my wife had with her car. We got a nice car that has an automatic braking system. Somebody kind of stopped short and turned into their driveway. Our car detected this as a problem. Instead of letting my wife get close but not hit the car, it slammed on the brakes automatically. It detected an imminent collision and said, "Oh, I'm going to slam on the brakes." Well, what happens? Well, she gets rear-ended by the person in the car that doesn't have that feature. So how do these smart features work with the new features? That's a big issue. So kind of coming back then, how long should a car last? How is that determined? Well, what is your consumer segment for that vehicle? If you have a low-cost consumer car, very small car, budget car, the expectation is that that probably won't last as long as a very fancy high-end car. Okay? So you can kind of set some durability requirements based on that. Consumer usage profiles. So a vehicle that's a truck may have a different usage profile than a vehicle that's a small car. And most car companies measure everything that goes on in a certain consumer's car. So they'll pick a consumer and they will say, we're going to instrument your vehicle. And they instrument that vehicle for that consumer, and then they measure everything that that consumer does to that vehicle. How many potholes do they run over? How many times do they slam the driver's door versus the rear right passenger door? All these things are counted and profiled by the consumer, and then they're taken to the statisticians, and then the statisticians come up with an estimate of a certain severity customer. And whatever it is, maybe it's the 99th percentile severity customer, the 99.9th percentile severity customer, or the 90th percentile severity customer. They usually don't design it for the average customer. They want it to last longer than that. If you're a reasonable consumer, chances are you're not going to have a problem with your vehicle. So you can think of any kind of probability distribution being usually a normal or some sort of curve like this, where you have certain consumers that are way out here. Maybe you have a really aggressive driver that likes to slam on the brakes, and they are a part-time NASCAR driver, and they just really are aggressive in their handling and performance, and they live on a bad road. They hit a lot of potholes. So maybe they're out here on this tail, whereas your average consumer might be over here where the loads aren't severe. So you decide we can't make a car that lasts forever, so maybe we're going to have the 99th percentile severity customer be our target, or the 90th percentile, or whatever it is that's usually designed out on this tail over here. Now, as part of that process, the statisticians come up with a durability schedule. So maybe, let's just pick one of these, maybe the 99th percentile severity customer, in his estimated extrapolated life of his car, it's 50 potholes, does 2,000 miles of rough road, does 75 twist stitches, and has 50,000 miles of straight highway. And there are any number of sub-classifications that you might have in a proving ground. Cornering, there's one test that General Motors does called a rock cycles test. You get out on a gravel patch and you floor it, and you put your car in drive, and then you take it while it's still floored and you throw it over to reverse. That is a huge hit to the structure around the engine. Okay, so that rock cycles test is a fairly severe structural test. So anything you can think of, there's probably some sort of proving grounds test that's associated with that type of usage characteristic. And some things that maybe normal people wouldn't do to their car, they might test for them at the proving grounds. So they come up with this durability schedule. Okay, so it's up to the test engineer and the test driver. And now the test driver can be a computer, because proving grounds are a great place to have automated driving on these proving ground roads. They used to have drivers drive a lot of these potholes and rough roads, and it's actually pretty hard on a body to be subjected to that all day long when you're bouncing up and down in a car. So now a lot of these things are automated. But the durability test engineer goes out and they don't do 50 potholes. They might do 1 or 2 potholes. They may not do 2,000 miles of rough road. Maybe they'll do 1 mile. Maybe they do 1 or 2 twist ditches. And the straight, well, they might not even do that, but they might do 10 miles of straight. And they measure the loads during all of this testing. These tests are actually pretty repeatable. And it's really amazing. I guess they wouldn't be really good tests if they were not repeatable. But the loads that you see for multiple passes on the same vehicle are fairly consistent when the testing speed and all those other type of variables are the same. Sure, there's some variation, but the variation between one rough road mile and the second rough road mile over the same stretch is not terribly different. There's other sources of larger variation. So you do all these different things. You send this over to the durability analyst. Let me make a little bit of room. And just as we've done with block cycle loading, the durability analyst calculates the damage per pothole, the damage per mile of rough road, the damage per twist, and the damage per mile of straight road, or whatever it is. And all these other different things that compose the durability schedule. The total damage then well, 50 times the damage per pothole, 2,000 times the damage per rough road, and you get the idea here. You add these things up and you come up with the total damage. And if these things are designed to the 99th percentile, then your damage should be less than the 99th percentile damage. Okay, you should end up with a damage less than 1 with whatever confidence level that you have in that statistical analysis of the usage. Okay, so this is how the durability engineer uses a proving grounds. Of course, like I said, there are many, many uses for proving grounds. It's not just for durability, but it tends to be one of the main uses for proving grounds, in my opinion, is from the durability. So the things that go into this durability schedule are really important, and they can change with the vehicle. But just like anything in industry, you kind of start with what you know and you modify it and you tweak it and you see how things go. There are lots of interesting things that go along with technology these days. Even many years ago, companies were scanning potholes. So they would find somebody that lives with their car near a road that has a bad pothole. Their car that's instrumented would send an alert. They would be able to pinpoint where that vehicle was, and they'll say, wow, that's a great pothole. Let's take a look at that. Let's measure that pothole, and that's going to be our new standard pothole from now on. So they make adjustments to their proving grounds based on measurements and data that they get. Same thing with rough road, a thing called Belgian blocks. They give that kind of cobblestone appearance, and you're kind of bumping up and down with low level cycles and stuff. So it's all kinds of interesting things. And you can probably tell from this lecture that I really think that That's a neat job, and I do think that my personal ambition was to be a professor, to teach and to do research, but it was really hard to leave General Motors when I did. But I think I probably made the right move personally. But if I could do it all over again and split my life in two, I definitely would have stayed as a durability engineer. All right, well, I think that's probably about enough for this lecture. But if you have questions again, please don't hesitate to contact me.